we're going to talk about non-parametric statistics. So non-parametric statistics are useful when you can't make the typical assumptions that help us do our parametric test. You might remember earlier we've always assumed things like we have a normal distribution or approximately normal distribution. In fact, as a little bit of a review here, let's take a look at X bar, your sample mean. There's a couple conditions under which the sample mean has a normal distribution, or at least an approximately normal distribution. What are those two conditions? Does anyone remember? All right, so if n is greater than 30, so if n is greater than 30, x bar sub n is approximately normally distributed. All right, so good. Someone else for the other condition. In what other way could the sample mean have a normal distribution? One more time. Yeah, if the population you're sampling from itself has a normal distribution. So if the parent population, no relation to me, if the parent population has a normal distribution. So those are a couple conditions under which sample mean would have a normal distribution. And from that, earlier in the book, we had a z-test and a t-test based on this kind of an assumption. But you can't always make that kind of assumption. So if you can't, then what do? Your tests don't work. In particular, when you're doing a chi-square test for variance, testing a variance or standard deviation, that test requires the assumption that you have a chi-square distribution, or that you're, let's see, let's see, the chi-square test. There's a pretty rigorous distribution. No, I think that it required that you have a normal distribution, and it was a very rigorous requirement. Some of these requirements aren't so bad as long as you have a good enough sample size, or the sample you're drawing from comes from a population that's at least symmetric. But if you can't do that, then we have to do something else, and those are our non-parametric tests. Now there's some advantages and disadvantages of our non-parametric test. So non-parametric test. Advantages. Advantage is that it's more widely applicable because you don't have to meet as many rigorous requirements. More widely applicable. And it can be used with non-numerical or categorical data. So again, that makes it easier to use in more circumstances. But there are some disadvantages. Disadvantages. A lot of times it'll waste information. Instead of using just the value, you might just use its rank. Instead of using, again, the value, you might just use whether it's positive or negative. So you're throwing out a lot of information. And something else that I'll have to define in a minute is that it's not as efficient. Not as efficient. So let's talk about the efficiency, what that is, and then take a quick look at, some efficiencies of some of our non-parametric tests. So your efficiency is basically how good it is compared to a parametric test. So let's take a look at a definition of efficiency. Efficiency is the number of observations required by a parametric test. So the number of observations required by a parametric test divided by the number of observations required by a non-parametric test to, say, reject the null hypothesis. So something that's extremely inefficient would have a very low number here. If something is relatively efficient, then this number is going to be closer to 1. So today in this first section, section 13.2, we're going to look at something called the sign test. Now the sign test really is just going to look at whether or not something is positive or negative, and then make a determination about a null hypothesis based on the number of signs that are positive or negative in a sample. So the efficiency of the sign test is 63%. Sign test, 63%. Does that sound very efficient? Not really. Sign test, like I said, wastes a lot of information. Now, each test that we can consider in Chapter 13 has a test that's equivalent to it in the parametric world. For the sign test, you can have an equivalent z-test or t-test. A better version of the sign test is something called the Wilcoxon sign rank test. And that efficiency is 0.95. So that's actually pretty good. Some other efficiencies, 2 independent samples. Again, we did that with z-test. Again, you can do that with a Wilcoxon rank sum test and get a 95% efficiency. We had dependent cases of paired data. We could do that with a parametric test. We could also do it with a sign test, etc. So there's a lot of different tests that we can do non-parametrically that we do parametrically. They just work a little bit different. In the case of the sign test, we're not going to be testing claims about a population mean. We're going to be testing claims about a population median. Okay, so how does a sign test work? Let's take a look at that. So this is the last of our Greek letters that we're going to learn. This one is called eta. So if you play words with friends, it's a good word with friends in a pinch because it only has 3 letters, 2 of which are vowels. Eta is the population median. So let's remind ourselves something. We have a final exam in a week. What is the median of a set of data? That's the middle number. So if you've got something that's the middle number, half the time you expect to be above it, half the time you expect to be below it. So if you hit the median right on the head, then if you're looking at what's above or below, positive or negative, half the time you should be below, half the time you should be above. In that case, you can do a nice hypothesis test. There's a couple different ways you can do it depending on what kind of data you have. Let's start with some data that's in the book, or at least one of the problems there. Now the nice thing about having StatDisk available to us is that we don't have to do this calculation anymore. You can look at this and kind of see that the way it's set up, if you have a large enough sample size, that is n is greater than 25, basically you're doing a z-test. You're doing z equals x minus the mean divided by the standard deviation. That's essentially what's happening here. Now the author writes it like this. I rewrite it a little bit easier like that. I think it's just a little bit more user-friendly to try and plug that in by hand. Of course, we're not going to have to worry about plugging that in by hand. Okay. So let's start with one of the homework problems, and if it's okay with you, I'll probably be doing a couple of your homework problems. We'll start with problem number 9. It says we've got 10 matched pairs of actresses and actors. The same year that they won the Oscar, they looked at their ages. The data are paired according to the years that they won. Use a 5% significance level to test the claim that there is no difference between the ages of Best Actress and the age of Best Actor. So we can do this a couple ways. The first way we're going to look at this, I'm not sure what's not letting me zoom in. Let's try this one. No. There we go. So the first way we're going to look at this is just by subtracting. We're looking at which one's bigger and which one's smaller. So in this case, Best Actor is bigger, 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 smaller, bigger, 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 bigger. In fact, there's only one year in which the Best Actress was older than the Best Actor. So, okay. Now, if you look at this, there's 10 pieces of data. We had 9 positive and 1 negative. The way you define that doesn't really make a difference. If you wanted to look at that in the other way and say, all right, well, we had 9 negative and 1 positive, it's still going to be an equivalent test. We're going to test the claim that actresses and actors come from a population with the same mean age. Now, if there's no difference between the age, then the median difference is 0. So the median difference, eta, is the median difference. So when I subtract the age of the Best Actor minus the age of the Best Actress, you know, it's going to balance out. I'm going to get 0. What's the alternative hypothesis? It is different than 0. There is some kind of a difference between their ages. We're going to test this claim at the 5% significance level. Let's go to StatDisk. Then down to Analysis. Over to Sign Test. Now, there's a couple ways that you can conduct this test, and I'll show you both of them. In the next example, I'll show you with given pairs of values. In this one, I'll give you how to work with given number of signs. We're going to test the claim that the median difference is 0, 5% level. We had 9 that were positive and one that was negative. Now, kind of behind the scenes, statistics is going to evaluate these in different ways. Depends on the total number of pieces of data in our data set. But that need not concern us. What's going to concern us is the p-value. So it's using basically the table and a critical value approach. Let's see, can we get... No, it's not going to let me do that. Okay, so guess we're going to have to look at table A7 real quick. Table A7 is going to show you how to decide whether or not to reject or fail to reject based on the size of our test statistic. The test statistic is going to be the smaller number of positive or negative signs. So let's flip over to table A7. At the bottom here, they give you the instructions on how to use this table. It says reject a null hypothesis if the number of the less frequent sign is less than or equal to the value in the table. We're doing our 5% test. So that 5% is divided up into two tails because it's a not equals in the alternative hypothesis. N was 10, so we can reject if the less frequent sign is 1 or 0. In this case, it is. So we had the less frequent sign, the number of negative signs was 1, so we can reject. Oops. I think our original claim was that there was no difference in the ages there. Let me just double check that. Yeah, there's no difference here, so this is our original claim. The original claim contains the condition of equality, and we rejected that original claim. So we're right here on our chart. There is sufficient evidence to reject the claim of no difference in ages. And that's as far as we can and should go with this because that's all we tested was for a difference or no difference in the median age. Now, as a little bit of a contrast to that one, we're going to move down to one that has a little bit more data, and the data is going to be in pairs. So that next one's going to be problem number 11. I'm not sure if you're going to want to try and follow along or not. It's going to be kind of up to you. But I am going to do a little bit of manipulation with Google Sheets. So the data set that we want to look at comes from here, 12th edition, POTUS. So it's the 12th data set down. what we're going to do is we're going to compare the height of the president to the height of his opponent in that year. So I think this is for the first 38 presidents. And what we're going to try and see is there a difference in their median height? That is, do we tend to elect a taller person president? Now, the problem we're going to run into, I think, is that a couple of these cells have missing data. I'm not really sure how to manipulate that out of our data set in StatDisk. So what I'm going to do is I'm going to copy these two columns into Google Sheets. Let's see. Let's try that again. And then delete a couple values there. So I think they want you to use copy up here, copy selected, and then you can paste that into Google Sheets. So this is not a bad exercise, really, to show you that, sometimes before you really get down to some analysis, you have to do some cleaning up of the data. You're not always going to get nice, crisp, clean data. So that's what we're doing here. For these pairs that don't have an X and a Y, or a presidential height and a candidate height, we're just going to delete them. So delete row 1. And then after that, I'm going to delete a couple more rows. Delete rows 3 and 4. I think there's one other place. Yeah, down here, we're going to delete that row. So what I'm giving myself then is a nice clean data set. A data set that has all X and Y values, presidential height, and his opponent's height. When you've got these, highlight all that, and we're going to go back to StatDisk and paste it in. So I'm going to copy this here. Back in StatDisk land, I want to clear out this whole data set. I'm done with this. I've got the ones that I needed. So I'm going to clear this out and then just paste in the data set that I just created. And now it's nice and clean. We're going to set up essentially the same kind of hypothesis test that we did before. And that is, we're going to test for a median difference of 0. Yeah, so this is problem number 11. If you look there, we do have down here we want to test the claim that there is no difference. So median difference of height of 0. H sub 0, eta equals 0, median difference. And the alternative then is that the median difference is different than 0. We'll do this test at the 5% significance level. We've already entered our data. So now let's see if we can't come up with some kind of a p-value from StatDisk. Let's go back to analysis, down to sign test. This time, instead of just telling it, well, how many positive and negative signs we had, we can actually let it figure it out. So what it's going to do is it's going to subtract, look at the sign and count them up, etc., and work with it through that way. But you want to click given pairs of values. And then it's going to ask you for the form of the alternative. We're going to be testing, actually it's going to give you median difference of 0. difference of 0. You know, I have to assume that it's going to be the null hypothesis here then. So it's a little bit different than maybe some of our other things. Let's test it and see what happens. Our two columns of data are already here. Our significance level is here. So evaluate. Okay. There's 32 pairs of data. 18 were positive, 14 were negative. So that means the smaller of those is your test statistic. So what's happening here is that, you know, I don't know, if things were even, nice and perfect, then out of 32 pairs of data, you would expect to be above the median, that is positive 16 times and negative 16 times. Our results are a little bit different, 18 and 14. Is 18 too far away from what you expected to be surprising? No, not really. So you got a couple more, but it's not really conclusive proof that we ended up with a statistically significant difference in the heights. You can see that based on the plot of the z-score. So they calculated the z-score was negative 0.530. So that's comfortably between our two critical values. Now, this critical value approach is not one that we've done in this course. It's not something I'm going to hold you responsible for. But what this is showing you is that because the value is in this, in between the two critical values, that we're not going to reject the null hypothesis. There's not sufficient data to reject the claim that the median difference is 0. So fail to reject H naught. There is not sufficient evidence to warrant rejection of the claim of a median difference of 0. Now, as far as an exam is concerned, or a final exam, I have to be pretty blunt about the description of the problem so that you would know to use a non-parametric test, for instance, like a sign test. It's not something that you're conditioned yet to looking for, and that's okay. I'm not going to try and trick anybody with a sign test type of problem. I might just say apply a sign test. So, in which case, you can just run it through StatDisk. For homework, try problems 1 through 13.